Okay, welcome back to the today's class. Today we will be seeing uh, what will happen if a AC current is passing through a resistor, capacitor, and inductor. Okay, how the graph gets changed, what the voltage will be, and how the current will be. We will see these things. First, the resistance, capacitance, and inductance are the three basic elements of an electrical network. In order to analyze any electric circuit, it is necessary to understand the following cases. So, if you take a power system or an electronic circuit or any systems which are operating through electrical or electronic, the three basic elements are resistance, capacitance, and inductance. We are having only these three elements as a basic elements. Other than we are having semiconductors. Semiconductors will also have a resistance in them and also have capacitance in them. So we need to study basically of passive elements such as resistance and capacitance. So we need to understand what will happen if a electric current, that is alternating current, passes through these elements. If we know what will be the reaction which will happen in this element, then it will be very easy to analyze and formulate a mathematical model, and we can understand the circuit very easily. First one is alternating current through a pure resistor circuit. Second one is alternating current through pure inductive circuit. And the third one is alternating current through pure capacitive circuit. Here the term pure represent the resistance is alone present in the circuit. No inductance or capacitance are present in the circuit. Similarly here, if you see it is a pure inductive or pure capacitive circuit, the circuit consists of only inductance or only capacitance. None other substances is present in the circuit. In all the three cases, it is assumed that a pure sinusoidal alternating voltage is given by the equation V is equal to Vm sin omega t is applied to the circuit. The equation for the current, power, and the phase shift are being developed in each cases. So for all the three circuits, we are going to apply a voltage to a resistor, inductor, and capacitor. And the mathematical model of the voltage being applied is V is equal to Vm sin omega t. Here the sin omega t term represents the alternating current as a pure sinusoidal waveform. And here Vm represents the maximum voltage peak available in the sinusoidal waveform. First, we are going to see the alternating current through the resistor. Consider a simple circuit consisting of pure resistance in ohms connected across a voltage source of V is equal to Vm sin omega t. You can see this is the simple circuit. Here only resistance is present in the circuit. Other than resistance, there is no element such as inductance and capacitance. See, this is the voltage V is equal to Vm sin omega t. This voltage is being supplied to the resistor. So while supplying the voltage in a closed path in a resistor, you can see a current I will be flowing in the circuit. As per Ohm's law, the equation of current I will be equal to V by R. You know Ohm's law, I is equal to V by R is given from the Ohm's law. Here you can substitute V is equal to Vm sin omega t because we are using a sinusoidal waveform of maximum magnitude Vm. So for V, you can substitute Vm sin omega t here. Then for a resistance, here the resistance value is R. So you can directly put R over here. So what you get is Vm divided by R sin omega t. Comparing with the standard equation, I is equal to Im sin omega t plus theta. Here you get the current which is flowing through this path is nothing but the current which we given through the voltage. That is, the voltage source will produce the current and pump the current into the resistance. So we will get the current, that is the maximum current is Im, and the current flowing through the circuit will be Im sine omega t plus theta. Here the theta term is added because uh, the current will be delivered by the voltage source with an angle. Okay. Next, we can see Im is equal to Vm by R. We know because of Ohm's law, I is equal to V by R. Here this current Im, that is the maximum current, will also be equal to Vm by R. And theta is represented as 0. Theta equal to 0. Why theta is 0 here is, if you connect a pure resistance in a pure sinusoidal waveform, then what will happen if you observe the voltage wave and the current wave in a digital oscilloscope? You can see the waves both are in phase. So you can say that theta is equal to 0. This indicates that the voltage wave and the current wave are in phase with each other. So there is no phase difference between the voltage and the current wave. So this is the waveform. If you see this waveform, this is the voltage and the current magnitude which is represented in y-axis, and in the x-axis it is marked in time period from 0 to 360. And this point is the pi point. Here it is the 180 degree and this is 0 degree. This is the wave, two waves. This is the current wave, which is I is equal to Im sine omega t, and this one is the voltage wave, V is equal to Vm sine omega t. So if you see these two waves through an oscilloscope, then you get these waves drawn. You can see that the two waves are starting at the same time at the 0 position and gets end at the same time at 180 degree position, and then it also again ends back at the 360 degree position. Both waves are starting at the same time and both waves are crossing 0 at the same time, and both the waves are ending at the same time. So if you need to measure the phase difference, you cannot do so. So only we said theta equal to 0. In the graph, the voltage wave and the current wave are in phase. Here in phase represents both starts at same and ends at same. Both the waves cross the 0 at the same time. This helps us to say the waves are in phase. When current is 0, voltage is also 0. You can see in the figure, when current becomes 0, voltage is also 0. There is no phase difference in both the waves, and the phasor diagram is shown in the below figure. You can see this is the phasor diagram of the graph. If you represent a voltage wave and current wave, you can write or draw a phasor diagram. Here you can see both the voltage wave and the current wave are in the same line. Okay, this represents the phasor diagram. If you cannot see any differences, in the next slide you can see the differences. The instantaneous power in AC circuit is given by the product of voltage and current. So now we are going to find the power which is delivered to the load, which is nothing but the resistance. Here we know that P is equal to V into I. Here V is the maximum voltage, which is nothing but Vm sine omega t, and I is nothing but Im sine omega t. What we are going to do is just going to multiply Vm Im sine square omega t. So we can apply the formula for sine square omega t. which is nothing but 1 minus cos 2 omega t divided by 2. So we get Vm Im by 2 1 minus cos 2 omega t. So you apply the formula for sine square omega t, which is nothing but 1 minus cos 2 omega t by 2. Okay, then now you are going to multiply this term inside this and also inside this. Vm Im by 2 minus Vm Im by 2 cos 2 omega t. Then the power equation will be like this. From the above equation, the instantaneous value of powers can be found. The constant power component present in the alternating quantity is Vm Im by 2, whereas the fluctuating power component present in the sinusoidal waveform is Vm Im by 2 cos 2 omega t. So you can calculate the average power, which is nothing but P average, which will be equal to Vm Im by 2. So here what we are going to do is we are taking root 2 into root 2. So Vm by root 2, Im by root 2. So this is nothing but the RMS values of the voltage and current waveform. If you divide maximum value by root 2, then you get Vrms. Similarly, if you divide the maximum current by root 2, you will get Irms. So the AC power, that is the average power, this is nothing but the RMS value of voltage and RMS value of current. So we know that the power average is equal to Vrms into Irms. So you can substitute Vrms is equal to I into R. Then you will get I square R. So this is same as Ohm's law. Okay, this is the next one, the alternating current through a capacitor. Consider a circuit consisting of pure capacitance C, which is measured in farad, connected across the voltage source, which is same, V is equal to Vm sine omega t. The current I charges the capacitor C. So in this figure, this is the voltage source, which is nothing but V is equal to Vm sine omega t, and this is the capacitor. The capacitor is connected in series with the voltage source. Now the current I is flowing through the capacitor. Due to this, the current will charge the capacitor C to its maximum value. The instantaneous charge Q on the plates of the capacitor is given by Q is equal to CV. You all know. The charge will be equivalent to C into V. So C into V, you can substitute Vm sine omega t, which is nothing but C into Vm sine omega t. Current is the rate of flow of charge. You know that thing. So I is equal to dq by dt. Here we have find q. So what we are going to do is differentiate the CVm sine omega t with respect to dt. So d by dt C Vm sine omega t. So now you will get I is equal to C Vm d by dt sine omega t. What we are doing here is you are taking the term CVm, which is constant. So you are taking out of differentiation CVm. Now you are going to differentiate d by dt of sine omega t. So while you differentiate sine omega t, you will get cos omega t, which is nothing but CVm. When you differentiate, you will get another one omega and cos omega t. After that, what we are doing here is you are taking the omega term out by dividing the terms. Okay, so we get I is equal to Vm 1 by omega c into sine omega t plus pi by 2. So we are converting the cos omega into a standard form into sine form. So what we are getting here is cos omega t is converted into sin theta. So what you need to do is sin omega t plus 90 degree, which is nothing but pi by 2. So cos theta is equal to sin theta plus 90. So this is the formula. You are applying this formula here. Sin omega t plus 90 degree. While applying this, you can say I is equal to Im sin omega t plus pi by 2. This term 1 by omega c is very small, so you can leave this term. So you will get I is equal to Im sin omega t plus pi by 2. So here you can see this Vm term and the 1 by omega c term has completely converted into Im term. If you need to understand this, you need to do a very long derivation. So these derivations are simplified. So we are directly putting Vm by 1 omega c into Im directly. After that, you will get the term sin omega t plus pi by 2, where Im is equal to Vm by Xc. Here, how Xc comes is, you can see here 1 by omega c is equal to Xc. Okay, so we are putting Vm by Xc. Okay, so this is nothing but Im. So Im sin omega t plus 90 degree. And here the terms are given here. Im is equal to Vm by Xc, where Xc is equal to 1 by omega c. So you can further extend this formula. Omega is equal to 2 pi f. So 1 by 2 by Fc. Okay. In the graph, the voltage wave and the current wave are not in phase. The current wave is purely sinusoidal and hence having a phase angle of plus 90 degree or plus pi by 2 radians, that is 90 degree phase shift. This means that the current wave leads the voltage wave. This is the graph. You can see this is the voltage wave, which is nothing but V is equal to Vm sin omega t, and this is the current wave, which is nothing but Im sin omega t plus 90 degree. So you can see this pi by 2 term is added in sin omega t plus 90 degree, but in resistive load we made only Im sin omega t and converted the theta term, which is sin omega t plus theta, and you substitute theta is equal to 0 for resistive load. But in capacitive load, while we observe the graph in the CRO or digital oscilloscope, you can see that the current wave is leading by an angle of 90 degree. So only you are getting Im sin omega t plus 90 degree. Here you can see the current wave and the voltage wave are not starting at the same time. That is, if the voltage wave is 0, current wave is not 0. See, for this instant here, the voltage wave is 0, but the current wave is at its peak. So, this represents there is a phase shift of plus 90 degree. And this phase shift is measured here, which is nothing but pi by 2. 90 degree phase shift is present from this point 0 point to this 0 point. This is the voltage 0 point and this one is the current 0 point. For while you make a difference between these two, you will get a 90 degree phase shift, which is plus 90 degree phase shift for capacitive load. The instantaneous power in AC circuit is given by the product of voltage into current. Here P is equal to V into I, and V is nothing but Vm sin omega t, and I is nothing but Im sin omega t plus 90 degree. Here we are going to substitute the formulas. Sin omega t plus 90 degree is equal to cos omega t. So you can substitute it directly. Vm Im sin omega t, and this term sin omega t plus 90 degree is converted into cos omega t. And we are going to substitute another one formula. 2 sin omega t cos omega t equal to sin 2 omega t. So what happening here is you are taking this term to here. Okay, so you get sin omega t cos omega t equal to sin 2 omega t divided by 2 over here. So you are having sin omega t cos omega t. So you need to substitute sin 2 omega t divided by 2, which will give you a equation of Vm Im by 2 sin 2 omega t. From the above equation, we can conclude that the pure capacitance never consumes power. So the power is never consumed by the capacitance. Capacitance always delivers the power. Hence, the average power consumption is 0. Similarly, this is the phasor diagram for the above representation of the graph. In this phasor diagram, you can see the voltage wave is present in the phase and the current wave is present. Here you can see the current wave is leading the voltage wave by an angle of plus 90 degree. Similarly, in case the voltage wave and the current wave are measured when a capacitance circuit, then the current wave will always lead the voltage wave. So if you pass an alternating current into a capacitance, then the current wave will lead the voltage wave in the capacitor circuit. Alternating current through inductor. Consider a simple circuit consisting of a pure inductance L, which is measured in Henry, connected across a voltage of V is equal to Vm sin omega t. The current I charges the inductance L. So this is the circuit. Here this circuit consists of only inductance. No capacitance or resistance is present, and this is the voltage source, which is nothing but V is equal to Vm sin omega t, and this voltage source is connected in series with the inductor, and the current I is flowing in the inductor. The self-induced EMF in the coil is given by E is equal to minus L di by dt. So the induced EMF, that is the voltage present in the inductor. So the induced EMF in the inductor is measured using the formula minus L di by dt. Here you can see the voltage V is equal to minus E. So you can substitute minus of minus L di by dt. So while substituting like this, you will get V is equal to L di by dt, where V is equal to Vm sin omega t, which will be equivalent to L di by dt. Here V is this one, so you are going to substitute Vm sin omega t equal to L di by dt. Next, you are cross multiplying all the terms. Di is equal to, you are making di over here and cross multiplying all the terms over there. So you get Vm by L sin omega t into dt. So to remove the differentiation, you need to integrate. So what we are going to make here is I is equal to integration of di, which will be equivalent to integration of Vm by L sine omega t dt. So while integrating, what you get here is the constant value is Vm by L. So remove the constant value out of integration. So while you integrate sine omega t dt, you will get minus cos omega t by omega. So after integrating, what you get the term here is minus Vm by omega L sine omega t minus pi by 2. So the cos omega term, that is minus cos omega t term, is converted into sine theta. To do that, the formula is cos theta is equal to sine theta minus 90 degree. So you get sine omega t minus 90 degree. As sine omega by 2 minus omega t equal to minus of sine omega t minus pi by 2. So you can substitute these things over here and you can get rid of the minus symbol. So I is equal to Im sine omega t minus pi by 2. Here, similarly, the Vm by omega L term is nothing but Im. Here you can see where Im is equal to Vm by omega L. So you can substitute Vm by omega L directly into Im. I is equal to Im sine omega t minus 90 degree. And here the omega L term can be converted into Vm by XL. Similarly, the omega term has another formula also. Omega is equal to 2 pi f. So XL is equal to omega L, and you can substitute omega is equal to 2 pi f L ohms. Okay, here XL represent impedance present in the circuit. So the current flowing through the inductance circuit is Im sine omega t minus 90 degree. In the graph, the voltage wave and the current wave are not in phase. So in this graph, you can see the waves, voltage wave and the current wave are not in phase. Both are not starting at the same time and ending at the same time. The current wave is purely sinusoidal and having a phase shift of minus 90 degree radians. Okay, so on comparing capacitance, inductance having a minus 90 degree phase shift. This means current wave lags the voltage wave. So when an inductance circuit, the current wave will always lags the voltage wave by an angle of minus 90 degree. If you see the phasor diagram, this is the voltage wave which is mentioned here, and this is the current wave. You can see the current wave is declined by an angle of minus 90 degree. For capacitance wave, you can see the current wave is in the upper direction, which is nothing but plus 90 degree. Whereas in the inductive wave, you can see the current is being declined in the phasor diagram by an angle of minus 90 degree. So you can say the power, the instantaneous power in AC circuit is given by the product of voltage and current. P is equal to V into I. You know that V is equal to Vm sine omega t, and Im is equal to sine omega t minus pi by 2, which is nothing but minus 90 degree. So you can convert sine omega t minus pi by 2 into cos omega t. Here is the formula. You can see sine omega t plus pi by 2 is equal to minus cos omega t. So what here you need to do is sine omega t minus of 90 degree here is equal to plus of cos omega t. So you can directly substitute this thing. After that, you get a minus symbol over here. So minus Vm Im by 2 into sine 2 omega t. How this come is sine omega t into cos omega t. Here in the formula 2 sine omega t cos omega t equal to sine 2 omega t. So you can make the 2 in the denominator and you get sine omega t cos omega t equal to sine 2 omega t divided by 2. So substitute the value for here. Then you will get minus of Vm Im by 2 sine 2 omega t. So the average power, to find the average power, you can integrate the complete setup for 2 cycles. That is nothing but 2 pi. Sorry, for a one complete cycle from 0 to pi, 2 pi. So integration of 0 to 2 pi minus Vm Im by 2 sine 2 omega t d omega t will give you a net result of 0. From the above equation, we can conclude that the average power consumed by an inductor circuit is 0. So the inductor circuit will not consume any power. When a pure sinusoidal waveform is passed into a pure inductor circuit, the power consumption is 0. Similarly, for a capacitive circuit, the power consumption is also 0 and the capacitor will not consume any power. When a pure sinusoidal waveform and a pure capacitance circuit is present, the power consumption in the capacitor circuit as well as in the inductance circuit is 0. Thank you.